Okay, so let's see if they're balanced. Well, the way we check these half reactions is first we check the atom balance, make sure that the atoms are okay. 6 hydrogens plus 6 hydrogens is 12. 12 and 12, that's right. 2 carbons is 2 carbons. 3 plus 1 is 4 oxygens, 4 oxygens. So the atoms are balanced. After I check the atom balance, I have to check the charge balance to make sure the charge on the left and the charge on the right agree. And so the charge on the left is 3 times neutral. 3 times 0 is 0. This is 0, so it's no charge on the left. This is neutral, so 2 times 0 is 0. This is plus 1, so 12 times plus 1 is plus 12. This is minus 1. 12 times minus 1 is minus 12, so plus 12 minus 12 is 0. And so net charge on the left is 0, net charge on the right is 0, the charges are balanced. Let's check this one over here. We have 1 manganese, 4 oxygens, 4 oxygens, 8 hydrogens, 8 hydrogens. So the atoms are balanced. Let's check the charge next. So this minus 1 plus 8 is plus 7. Plus 7 minus 5 is plus 2. Over here we have plus 2 plus 0 is 0. Plus 2. And so plus 2 on the left, plus 2 on the right, we're balanced. Okay, so the half reactions are balanced. Okay, the next step is to add the 2, except, these are half reactions because the electrons have to go somewhere. We can't have 3 electrons. And so if we produce 12 electrons here as product and we consume 5 electrons here as reactant, then there's 7 electrons that aren't going anywhere. And we can't have that, so we got to make sure the electrons cancel. And so the easiest way to do that is to just cross multiply. 5 over here and 12 over there. And so 5 times this will give me 60 electrons here. And then 12 times this will give me 60 electrons here. So I consume 60 electrons and I produce 60 electrons. So the electrons cancel each other out. All right, so let's go ahead and add everything up. 5 times 3 is 15 H2O plus 5 ethanol. Okay, this is product. I want to put all the reactants on the left. And so the next reactant would be 12 permanganates plus 12 permanganates. Plus 12 times 8 is 48 H plus. 12 times 5 is 60 electrons. And so these are all the reactants here. Then I'm going to combine all the products. And so that's 5 times 2 is 10 CO2s. 5 times 12 is 60 H plus. 5 times 12 is 60 electrons. Okay, 12 times 1 is 12. Mn2 plus, and 12 times 4 is 48 H2O. Okay, what we want to happen here is we want the number of electrons consumed, 60, to be equal to the number of electrons produced, 60. And so redox reaction is called an electron transfer reaction because electrons are transferred from the electron-rich species to the electron-poor species. Let's take a look. Well, there's some other simplification that we can do here. So for example, here we have 48 H pluses on the left, we have 60 on the right. And so we'll just change this to 12. All right? 60. We have 15 waters here, so let's get rid of those, because we have 48 over here. And so that would be 33. All right, so let's go ahead and write this out. This would be 5 ethanol plus 12 permanganates yields 10 CO2 plus 12 H plus 12 manganese 2 plus 33 H2O. All right, let's make sure it's still balanced. This would be 5 times 2 is 10 carbons. This is 10 carbons. We've got 6 hydrogens here. 6 times 5 is 30. 30 hydrogens here. Ooh. What do I have here? I got 45 hydrogens. Which one? On the left, 48. 5 times 12.
No.
Oh, to the right? Oh, 12 times 8. Oh, I missed that. 12 times 8 is 96. Where did I get 48 from? I screwed that up. So anyway, this should be 96 H pluses. 96 H pluses means that this is wrong. 60, I should eliminate all 60 of those here and make this 36. Is that right? 36 H plus. And so that means these 12 aren't here, and I should have plus 36 H plus here. Okay, so let's see if that fixes it. And so I get 5 times 6 is 30. 30 plus 36 is 66 H pluses, or 66 hydrogens. Over here I have 33 times 2, which is 66 hydrogens. So the hydrogens are balanced now. 66 hydrogens, 66 hydrogens. Oxygens, I got 5 there and 48 here. 5 and 48, be 53 oxygens. And so here I have 20 plus 33. 20 and 33 is 53. So 53 oxygens, 53 oxygens. And then 12 manganese. 12 manganese. And so the atoms are balanced. That checks out. And then I have to check the charge balance to make sure the charges add up equally on both sides. So this is 5 times 0. This is 12 times minus 1 is minus 12. Minus 12 plus 36 would be 24. Plus 24 on the left. This is 0. This is 12 times plus 2 is plus 24. This is 0. So plus 24 on the left, plus 24 on the right, and it looks good. Okay, I just rewrite this one more time. Let's just rewrite it just to make it look okay. So the balanced chemical equation would be 5 ethanols plus 12 permanganates plus 36 H plus yields 10 CO2 plus 12 manganese 2 plus 33 water. Does this look familiar, this process? No? Everybody should have done this in Chem 4. You know, this is a standard skeleton redox, balancing skeleton redox. Also in Chem 4, this is what we call acidic or neutral solution, balancing skeleton redox in acidic or neutral. If it's not specified, then assume it's acidic or neutral. If I would have specified that this reaction occurs in basic solution, what would you have to do? Some extra steps. If this reaction occurred in basic solution, then what we have to do is we have to get rid of H plus. H plus is not stable in basic solution. And so if there was a specification for basic solution, then we would have had to do this step. You know, if we had 36 H pluses, we would have had to neutralize that with 36 OH minuses. Those OH minuses come from the basic solution. Well, 36 H pluses and 36 OH minuses gives me 36 H2Os. And so here in basic solution, this H plus would have been converted into H2Os. Well, I just screwed up my balance because if I add 36 OH minuses to the left, then I'm missing a whole bunch of oxygens and hydrogens on the right. And so if I add 36 OH minuses on the left, I need to add 36 OH minuses on the right to make sure everything stays balanced. Do you guys remember doing this in basic solution? No? If not, go back and take a look at the Chem 4. What we're going to do is we're going to kick it up another notch. So I'm going to expect a little bit more than just repeating what you did in Chem 4. You know? And that little bit more has to do with driving force. We know that there's a driving force that's present here. And so let's talk about the driving force for redox reactions. The driving force for redox is we go from stronger to weaker. Stronger means more reactive. Yeah. Weaker means less reactive. Stronger means more reactive, less stable. Weaker means less reactive, more stable. And so essentially we're going from less stable to more stable. Well, what? Well, what it is it's going to be what we call an OA, RA to weaker OA, RA. Now what an OA is and an RA, OA just stands for oxidizing agent, RA stands for reducing agent. When we look at this, and I look at ethanol, ethanol did what in the reaction? Ethanol supplied the electrons. And so something that supplies electrons we call the reducing agent, or the RA. The oxidizing agent, or OA in this case, would be permanganate in H+, would be our OA. That's what takes the electrons. You can see this in the half reactions most easily. Looking at the half reactions, you see that the RA always produces electrons when it undergoes a reaction. And so this reducing agent produced the electrons here. The OA, permanganate acid, is going to consume the electrons. So oxidizers are electron poor, they want electrons. Reducers are electron rich, they give up the electrons. So what we're going to do is we're going to use the conjugate relationship. Do you know what conjugate pairs are? A conjugate acid and base pair. Have you heard of that before? Yeah. You should have heard about conjugate pairs. So for example, HCl is the acid, but do you know what the conjugate base of HCl is? HCl is the acid, and the conjugate base actually turns out to be chloride. So this is what we call a conjugate pair, HCl and chloride. Do you know about the strengths of conjugate pairs? For example, if the acid is strong, the base will be strong, weak. If the acid is strong, its conjugate base will be weak. And so here, it makes sense because if HCl is a strong acid, it gives up its hydrogen easily. It's H+. That means, does chloride have a strong attraction for hydrogen ions? No. And so in order for this to be strong, the chloride has to have a very weak attraction, otherwise it wouldn't let it go. And so that's the conjugate relationship. We can often think of these reactions as two-way, you know. We have the forward reaction, okay? And then we have the reverse reaction like this. So one side is strong, the other side is weak. That's what we're going to see for oxidizing agents and reducing agents as well. If we imagine this reaction occurring backwards, like this, then CO2 is what? Electron rich or electron poor? CO2. Yeah, it would be electron poor, because going backwards, CO2 and H plus consumes electrons. H plus, the oxidation states don't change, they're all +1. It's the carbon, that changes here. And so CO2 is, in H plus, will be our oxidizing agent. Now the conjugate relationship is like this. If this is strong, then its conjugate must be weak. So is CO2 a weak? Well, it depends on how strong ethanol is. Do you think ethanol is a fairly strong reducing agent? Is it pretty flammable? Yeah. It's a good fuel, so ethanol is pretty strong. We know CO2. I mean, is CO2 on that chart there? Is CO2 on the chart? No. CO2 is not on the redox chart. If CO2 is not on the redox chart, then how can we tell how strong or weak it is? Well, for CO2, you're going to have to use some factual knowledge. Is CO2 a good oxidizer? So let's compare it to oxygen. What's a better oxidizer, oxygen or CO2? Oxygen. In fact, have you heard of fanning the flames of a fire? Have you ever fanned the flames of a fire? What happens? The fire grows bigger, right? Why? Because you're feeding more oxygen to the fire, more oxidizer. But you might also have a CO2 fire extinguisher. If you have a CO2 fire extinguisher, then why doesn't the CO2 fan the flames of the fire? It doesn't make sense, because if CO2 is an oxidizer and you're trying to put the fuel out, the fire out, then how are you going to do it with CO2 if CO2 is an oxidizer? Like O2. It turns out that CO2 is an extremely weak oxidizer. And so CO2 can be used in fires, wood fires, paper fires, that kind of stuff. And since CO2 is such a weak oxidizer, it's not going to support combustion. Unless it's a metal fire, okay, you never want to use CO2 on a metal fire. Why? CO2 on a metal fire, because CO2 is an extremely weak oxidizer, but metals are very strong reducers. And so a metal can react with CO2. And so if you were to use a CO2 fire extinguisher on a metal fire, that would be like fanning the flames of a fire. You'd be feeding it more oxidizer. And so anyway, this is weak. That means ethanol is going to be strong. Permanganate This is the oxidizer, permanganate and H+. That means manganese 2 and water must be the reducing agent if we went backwards. Okay, so going forward it consumes electrons, going backwards it produces electrons. And so we could think of these half reactions as going either way. This reaction occurs, and so we could do this. Ethanol, this is going to be our reducing agent. Permanganate and acid, this is our oxidizing agent. CO2, this is our oxidizing agent. Manganese and water, this is our reducing agent. And then we can compare. If we compare the two oxidizing agents, permanganate versus CO2, which one's stronger? Permanganate in acid is stronger than CO2. And so we see for sure this is a driving force here. And then the reducing agents, ethanol is much easier to burn than manganese 2 ions. And so this is stronger, this is weaker. And so our driving force here is we're going from stronger to weaker. OA. It's stronger RA to weaker RA. Sure. And so we can kind of rank these, you know, a lot of these we kind of know what their relative strength is. CO2 is pretty unreactive. Okay, so this would be like an additional step we do for Chem 1A. All right, those are skeleton redox. Skeleton redox, we don't have to predict the products because the products are given. The next type is we're going to be predicting the products of reaction. Some of these you've already done, like this. Element plus element redox reaction. And so we might have sodium element plus chlorine gas, 2 elements here. What would form if we were to mix sodium and chlorine? Sodium chloride. We need to balance it. It should balance. Is there a driving force for this? In Chem 4 you probably didn't. You just mixed the elements and then got the charges and then balanced it. That's it. But in Chem 1A we'd look, you know. Sodium, are those electron rich or electron poor? Sodium metal. All right, chlorine, electron rich or electron poor? Who do you think loses electrons? Who do you think gains electrons in this particular reaction? Well, metals are electron rich. You know, this is why you don't want to use CO2 in a metal fire. Why? Because CO2, even though it's a very weak oxidizer, metals are so electron rich, you can have a nasty reaction. You don't want to use water in a metal fire either, because water can be an oxidizer as well. You use water to put out a lithium fire at a battery plant and burn down the whole plant. And so this is electron rich, meaning it's a reducing agent or oxidizing agent? Chlorine? is what? Our oxidizing agent. This is going in the forward direction. What's the oxidizer and reducer in the reverse? You know, what we're looking at is a competition. Which side is more stable? If the reactant side is more stable, then there should be no reaction. If the product side is more stable, then there should be a reaction. You know, what we want to do is we want to form, or we want to favor the side that's more stable. And so which side is it in this case? Well, let's look at the reverse reaction and take a look at the species. We have sodium ions and we have chloride ions. Going backwards, what would sodium ions act as? Are they taking electrons or losing electrons? Going backwards. They're taking electrons. So this is our oxidizer, this is our reducer. Then we compare chlorine gas or sodium ions. Which is the better oxidizer? Chlorine gas or sodium ions? Yeah, chlorine gas. Sodium ions are totally, fairly unreactive. Sodium metal or chloride? What's more dangerous to put? Sodium metal. And so we have a driving force here. In Chem 4 we didn't talk about it, or I didn't talk about it. What other types of reactions do we have? We could have things like sodium and oxygen. What should this form? Sodium and oxygen should form sodium oxide, which has the formula Na2O. Well, it depends on the conditions. Peroxides can form sometimes too, but we'll take it all the way to sodium oxide. The same type of situation here. You know, there's a driving force. It's element plus element. Redox. These were early on in Chem 4, element plus element. Then later on, you got the single replacement reactions. With single replacement reactions, you memorized a pattern. What was the pattern? The pattern for a single replacement was A plus BX yields what? AX plus B. You remember this one? In Chem 1A, the single replacement pattern could get you in trouble. Because in Chem 4, did you memorize any exceptions to this? No? Then you would get in trouble, potentially, because it doesn't always work. There are a lot of exceptions to the single replacement pattern, which if you don't have memorized, means you could end up with the wrong answer. Now let's look at an example here. Single replacement reaction. So you can take silver solid plus HCl, AQ. Silver and hydrochloric acid, what should form? Well, single replacement, A plus BX, yields what? Well, A plus BX yields AX, which would be silver chloride, plus B. B is H. But H doesn't exist alone. It exists as diatomic molecules. And so we should form molecular hydrogen. Silver chloride is not soluble in water. It's insoluble, so I wrote a solid there. Let's balance this. Different ways I could balance. I could use fractions or you could use whole numbers. Just multiply the whole thing through by 2. looking at this particular reaction, we got to see, is there a driving force present? This is a redox reaction. And so for single replacement, you looked at the activity series. The activity series, you compared the two elements, silver versus hydrogen. Which one's more active? More active means more reactive, which means less stable. So which one of those is less stable? Silver, metal, or hydrogen gas? What would you do if somebody gave you 10 pounds of silver metal versus 10 pounds of hydrogen gas? Which one would you take? If you take the silver metal, I think you'd take the silver metal. Why? Because, or somebody offered to fill your car up with some silver or fill it up with hydrogen gas. What would your preference be? Yeah, silver. And so, in other words, this is less active on the activity series. Less active means more stable. This is more active. More active means less stable. And so we're going from something that's more stable to less stable, which means that we should get no reaction. No reaction. Based on the activity series. Do you remember these type of problems? Yeah. Let's do the next example here. Silver metal plus nitric acid. Silver metal plus nitric acid should yield, well, this is an A plus BX pattern, so what should this give us? AX would be silver nitrate. Silver nitrate, unlike silver chloride, is soluble in water. And hydrogen. Hydrogen doesn't exist as monatomic or atomic hydrogen, diatomic hydrogen, H2 gas. Okay, let's balance this. I can use whole numbers this time, 2, 2, 2, and 1. Do we have a reaction here? Well, it's the same thing. We compare silver with hydrogen. We expect NR, no reaction, NR. Cancel those out. So on the one hand, double replacement's correct. NR is right for single replacement. We aren't going to get this product, but NR is wrong because a reaction actually occurs. There is a reaction. Now, did you memorize this exception? How many of these exceptions are there? A lot, depending on how you memorize it. One way to memorize this exception is to note that there's a big difference between hydrochloric and nitric acid. A big difference between these two acids. Well, you might say, what are you talking about? Because both those acids are strong acids. Well, that's correct. Both of them are strong acids. But one of them we call a mineral acid. You know what we call the other? An oxidizing acid, right? Nitric acid is what we call an oxidizing acid. Oxidizing acids behave differently than mineral acids. Why? Well, the reason is because of this. How do you recognize oxidizing acids? You look at the oxidation states here. Then maybe we can see it. So HNO, H goes first at +1, then O at -2, and that means nitrogen's at +5. HCl here, H goes first at +1, and then Cl at -1. Do you see a big difference there? Both of these have H+. H plus here, H plus here. Do you see that? H plus is a decent oxidizer. If we go back over to the chart over there, you can see it is a decent oxidizer. Or maybe not so decent. Go. Find it as there's H plus here. H plus is on the other end of the strength spectrum. It's on the weaker end, right? It's moderately weak. And so both of these have H plus present, but this one's different because this one has nitrate, this one has chloride. So all acids have H plus. The difference lies in their anion. And so the difference between an oxidizing acid and mineral acid is based on their anion. So what's the difference between these two anions? Well, basically the difference is this. Oxidizing acids are going to be much stronger oxidizers than mineral acids. Mineral acids are moderate, weak oxidizers. Oxidizing acids are powerful oxidizers. And oxidizing acids are powerful oxidizers because of what? Because of the charge on this. You know, chloride, is chloride a very good oxidizer? No. Chloride's already got its electron. How about this? Is nitrate a pretty good oxidizer? Yes. Why? Nitrate's a good oxidizer because the charge on what? Of nitrogen. Nitrogen is supposed to have how many valence electrons? It's supposed to have 5 valence electrons, right? How many valence electrons does nitrogen have in this structure? 0. How many plus 5 nitrogens do you know? Probably none. You know? And so this is a very high oxidation state. In other words, nitrate is a very powerful oxidizer. What's the difference? And so there's actually reaction here. Now, what is the reaction that occurs here? Well, one thing is you can memorize these things. You know, mineral acids don't behave the same as oxidizing acids. If you have an oxidizing acid, you can't put it into this form, right? There are other forms too. You know, there's more than one form of this single replacement. There's the X2 plus BY form, or AY form. Have you seen this one? Let's do X2 plus BY. Have you seen this? We need the X2 plus BY form because if we have a reaction like this, I take chlorine plus sodium bromide. Chlorine plus sodium bromide, does it fit this pattern here or does it fit this pattern here? It fits this pattern. And if it fits this pattern, then we reacted with 2 BYs to get 2 BXs and a Y2. Have you seen this? This is the second single replacement form that we have. And so we have at least two single replacement form or patterns, and exceptions to those. Chem 4 is kind of nice because Chem 4, you know, they never give you an oxidizing acid in there. Never. Why? Because you get a wrong answer. Right? They want you to get the wrong answer. And so they eliminate it. In Chem 1A, they don't care if you get the wrong answer, right? And so they might throw in a reaction that is an exception. And so how do we handle it? Well, do you want to memorize oxidizing acids and mineral acids, or do you just want to figure it out? We just want to figure it out. And so rather than using this form, the single replacement, we're going to use an alternate form of solving redox. Alternate form takes more time. And so if you know that, this is not an exception, I can just go ahead and use it, then single replacement for sure is faster. But if you don't know the exceptions, then you should play it safe and do the alternate method of solving redox problems. And the alternate method is what we'll talk about next time when we get there.